Problem 7.21. Prove the following inequalities. And we have three different inequalities, and the problem gives us a hint. In all cases, try to minimize the appropriate function. Okay, so let's see what they mean by that. So we have a is 1 plus x to the a is greater than 1 plus ax if x is greater than minus 1 and a is greater or equal to 1, which is called Bernoulli's inequality. So if you remember in our first unit when we talked about induction principle, we said we proved this thing, 1 plus x to the n greater or equal than 1 plus nx when n is a natural number, right? For all numbers, natural numbers. So this is just the generalization of that inequality for real numbers. So a are real numbers here, right? So let's see. This inequality can also be expressed like this. 1 plus x to the a minus ax minus 1 is greater or equal than 0, right? And we can say that this function, this expression, we can call it a function f, or function 1 plus x to the a minus ax minus 1. So this inequality is the same as saying that my function f of x is always greater or equal than 0, right? And so how do we check this, right? Well, let's see. Let's compute its derivative. When it says try to minimize the appropriate function, well, we can try to find the minimal value for this function, right? This is going to be a differentiable function, as we can see, because these are all well, this is not a polynomial strictly because it's raised to a power that's not integer, but those are combinations of polynomials or continuous and differential functions. Okay, so the derivative of this f prime and x is going to be a times 1 plus x to the a minus 1 minus a. Okay, that's the derivative. Sorry. And so the extrema of this function are those points where the derivative is 0, right? We have seen that before. So this is equal to say that a times 1 plus x to the a minus 1 equals a, right? Or in other words, that 1 plus x to the a minus 1 is equal to 1. Okay? Now what happens if a is greater or equal than 1, it says here, right? Then the only point where this is possible, right, is, well, we can say that, you know, 1 plus x is equal to 1 to the 1 divided by a minus 1, right? And in other words, x equal to 1, well, 1 to the 1 divided by, it doesn't matter, it's 1, right? So we have 1 plus x equals 1. In other words, this means that x has to be 0. So the only point that makes the derivative be 0 is 0. Okay, so what's the value of f at 0? So f at 0 is going to be 1 plus 0, 1, to the a, 1, minus a times 0, 0, minus 1, which is 0, right? So the function is 0 at 0, right? Now what happens with the derivative, right? Well, the derivative for every value x that's positive, this thing is going to be positive, right? So this is equal to a times 1 plus x to the a minus 1 minus 1, right? Now this is going to be positive because 1 plus x to the a minus 1 is an increasing function, and when x is positive, this is greater than 1, right? So f prime is greater than 0 when x is positive. It's easy to see that f prime is smaller than 0 when x is negative. So when we have 1 plus x to the something, if x is negative, this is smaller than 1, so to the something is going to be smaller than 1 as well. So minus 1, this is negative, right? So this is actually a minimum point. Okay? It's a minimum of the function, because the minimum of the function is at 0, and it's a global minimum because it's the only one, and the function is differentiable everywhere. That means that this function is going to be greater or equal than 0 for every x, which means that this inequality is true, which means that the original inequality is true. Okay? Let's see the second expression. So b, e to the x greater or equal than 1 plus x for all x in R. Okay, this means for all. Now again, we call this function e to the x minus 1, and what we need to prove is that f of x is greater or equal than 0, right? Now the derivative of this function, again, this is a differentiable function everywhere. This is e to the x minus 1. And the question is, where is f prime 0? Well, whenever e to the x is equal to 1. In other words, when x is 0, the derivative is 0, right? F prime at 0 is 0. Okay? What's the value of f at 0? F at 0 is 0 because e to the 0 is 1 minus 1, 0. Okay? Now, f prime is e to the x minus 1. We know that e to the x is greater than 1 when x is positive. It's smaller than 1 when x is negative, right? So this is going to be a minimum, just like before. Okay? So this is an absolute, 0 is an absolute minimum of this function, which means that this inequality holds for every real number. Okay? Now let's go for 3, part C. X divided by 1 plus x is smaller or equal than log of 1 plus x, smaller or equal than x, if x is greater than minus 1. Okay? As we have seen before, these are two different inequalities. Let's go for the first one, right? So the logarithm of 1 plus x is greater or equal than x divided by 1 plus x, if x is greater than minus 1. Okay? So it's the same as saying that a function f called the logarithm of 1 plus x minus x divided by 1 plus x is greater or equal than 0. Okay? If x is greater than minus 1. Okay, again, it has to be because the logarithm is not defined otherwise. Now what's the derivative of our f? The logarithm of 1 over x, the derivative is 1 divided by 1 over x. And then we have minus 1 plus x squared times the derivative of this times 1 plus x minus x minus x times the derivative is, so this is minus x. Okay, so we have this, right? 1, and then we have a common factor 1 over 1 plus x. This is 1 minus 1 over 1 plus x, right? Then we can expand this, take them to the same, yes, well, this is the same, yeah, the same denominators. We have 1 plus x minus 1, this is x, right? Or in other words, this is x divided by 1 plus x squared. Okay? This is obviously only going to be equal to 0 if if x is 0, so the derivative is only 0 at 0. And if it's always obviously positive when x is positive and negative when x is negative, because the denominator is square, right? So it is obviously a minimum of the function. What happens with this function is 0, right? F at 0, the logarithm of 1 plus 0 is 0, minus 0. Okay, so this is 0. So we have proven this inequality. Okay, the first one, for every x, so that x is greater than minus 1. Okay, let's go for the other one. So we have that x is greater or equal than the logarithm of 1 plus x. Then we have our function f is going to be x minus the logarithm of 1 plus x greater or equal than 0. Right? Now we differentiate this function. We have 1 minus 1 divided by 1 over x, which is the same as 1 plus x minus 1 over 1 plus x. In other words, x divided by 1 plus x. Right? Now if x is greater than minus 1, then this thing is always positive. And so, so again, the derivative of this is only 0 at 0, right? This is the only point where it's 0. And then if x is greater than or equal than -1, then this is positive when x is positive and x negative when x is negative. So this is a minimum again, and the value of f at 0 is 0. So we have proven this inequality for every real number. Okay, so all three examples are the same